And there we go. Off we go. It's looking a little tilted, actually. I don't think there's anything I can do about it. All right. We've got a homework due today, and that is homework number 4, and it's due tonight at midnight. This has timers and interrupts on it, and we went through some of this stuff before, and I was wondering if there were any questions. Questions on homework 4? You guys finished homework 4? It was all about timers and interrupts. So now that we know about timers and interrupts, let's go on to topics in homework 5. So homework 5 will be due next week, end of day on Thursday, and it is already posted onto the Blackboard system. And homework 5 has 26 questions, which when printed comes to 24 pages. So that's sort of a lot, I guess. And so what I'll do is I'll start off by asking some basic questions in the sense of a kind of a review. Let's change colors a little bit. How's that? Let's do this one. Port C is an 8-bit quantity which has a literal that you can set. And this will allow you to set the inputs and outputs on port C. And what we're going to do is use a vertical bar and an equal sign and set it equal to 0x01. What does that do? What does that do? This is like a basic sort of, I guess you might say, bit flippy kind of low-level programming question that you will encounter because you're going to see code that looks like this. First of all, when you see something like this operator here, well, it's really a shortcut for that, with a vertical bar, or maybe just continuous vertical bar. So what is this vertical bar we're looking at here? What is that? Yeah, this is a bitwise inclusive OR. Inclusive. Inclusive because I forgot how to count. I forgot how to count. Or exclusive is 0, 1, 1, and excludes 1 and 1. But or inclusive is different because it's 0, 1, 1, 1. So there it includes the case where you have 2 1s in a row, and then that's included. So this is a bitwise inclusive OR. And what's that do? 0x01. What's that? What's that mean?
Well, it's for the binary and X is wild card.
This is X, meaning hexadecimal.
Oh, yes.
Hexadecimal. So in 8-bit world, we'd write 0, 0, 0, 0, 0, 0, 0, 1. 0, lowercase b, to show that it's in binary. And this is a valid input literal for your code, as well as 0x01. Take that, do a bitwise inclusive OR with port C. Port C is 0B101101110. bitwise inclusive OR, what does it do? Bitwise inclusive OR. See, 0 plus 1 is, here, you see, 0 plus 1 is 1, right? So it's 1. And then this is 0 plus 1, 0 plus 1, 0 plus 1, 0 plus 1, right? So what does it do? This comes through, this comes through, this comes through, this comes through, this does not, this comes through. And now we're going to set it equal to port C. What has changed? If this was port C to begin with, and this is 0x01, what did we do? We set the least significant bit. That's what we did. So what does this do? It sets bit number 0. That's what this does. Sets bit 0. That's a basic bit operation. You want to set bit 0, this does that. What would you like to do if you wanted to set bit 1?
You will use the hexadecimal 1 after your 0x.
You could do this. Port C bang equals 0x01 shift, and now you can shift it over by 1 bit. Right? And now you're going to set bit 1. You should shift it over by 2 bits, you set bit 2. So this will allow you to set an arbitrary bit. That's what this does. And that is the answer to question 22. And you're going to see this code because you're going to have to do bit flipping in order to make the devices work properly. Let's do it again, only this time with a difference. This time what we're going to do is we're going to change this operation to up arrow equals. What does this do? What does it do? Let's do it again now, only this time we're going to rewrite the entire thing. So up arrow equals, you got a question? Is equal to port C up arrow. What's this up arrow do? Anybody out there in Zoom land? I got to see that there's people here. Are there people in Zoom land? Oh, there's a bunch of people out there. Anybody in Zoom land would like to take a stab at this up arrow thing? Well, up arrow, that's exclusive OR. So that's this operation here. So now I've got this whole bit vector up arrowed with this 1. If it's 1 and 0, the output will be 0. But if it's 1 and 1, the output would be, I'm sorry, if it's 1 or 0, the output is 1. But if it's 1 or 1, the output would be 0, because that's how exclusive OR works. So in other words, I switched from inclusive OR to exclusive OR when I switched from vertical bar to up arrow. That's all I did. But by switching that one thing, what I have done is I have taken the 0 and turned it into a 1. But if it were a 1, it would turn it into a 0. So this has the effect of toggling the least significant bit. So that does a toggle. And if you wanted to toggle not bit 0, but bit 1, then you could proceed to do this operation. And now you can toggle bit 1. In fact, you can toggle any bit you like to using the shift with the 0x01. You may have had CS131. I don't care. They didn't teach you this there. I know they didn't, right? And so this is the first time you're seeing this kind of code, but you will see it all the time when you start to look at code where they try to drive actual chips. Because when you drive actual chips, you're writing a device driver. And when you want to have that interface between the software and the hardware, knowing how to flip the bits to make the hardware do what you want is critical. This is how you control the actual real world. And you've got to be able to know when you look at this code what it is, what it means, or else you can't have a reading knowledge of the code. So now we know something about digital design 1. What other operations do we know? We know OR, we know exclusive OR. There's another operation that we may have heard of. It's called AND. Maybe AND we put in here like this. But that's the bitwise operator in C, C++, Java, C#, and maybe a few other languages too. I don't even know how many languages use that. So that would be 0, 0, 0, 1. That's what that does. So now we go back over here, right? And we say, what does this do? We put the ampersand in there. What does it do? Well, it does the same thing as this. It says port C is equal to port C and 0, 1. So what will the output be if the operation is and? And the answer is, well, whatever this is over here, it's all zeros. So 0 and anything is 0, but 1 and whatever this is going to come out. And so what it's doing is it's giving you the least significant bit. It's giving you bit 0, which in this case will happen to be a 0. And if you wanted to, you could get access to any bit just by shifting over. This will give you bit 1. You can go over to bit 20, whatever bit you want. So this is a way in which to obtain bit 0. Suppose you wanted to clear bit 0. Clear bit 0. Clear bit 0, but not clear any of the other bits. Not clear any of the other bits. Let's try this one. You're going to like this. Tilde. What does tilde do? Yeah, that's the complement. So it's the bar or the little tick mark. And so then if it's tilde on, we'll call it y, then what we'll do is we'll write 1, 0, 1, 0. Because tilde only takes a single argument. What would it look like if you wanted to use tilde over in here? Right, so you ended with tilde 0, x 0, 1. And the answer is, this is going to be all 1s. Except for this one, it'll be a 0. So now, what's the output look like? And the answer is, everything in the most significant bits will be preserved, but the least significant bit will be cleared. So now we've cleared the least significant bit. So this little idiom, well, I guess you write this one. Ampersand equals tilde 0x01 clears the least significant bit. And you can clear any bit you want to if what you do is say ampersand tilde, make sure that has priority, and then shift it over any bit you want. This will clear bit 1. You can clear bit 2, 3, 4, any bit you want to, you can clear it.
Just
Just
if
by
you
using.
wanted to just return the bit you're clearing and not the whole string.
Well, that's when you use the mask. That's when you use and that'll just give you one of the bits.
But wouldn't you have to do it as 2 steps?
You-
So
you
yeah,
wanna-
you do and first, and then you do till.
If you want to get bit n, you're going to have to get a 1, shift it over n times, mask it, and then shift it back,
Yeah.
and that'll give you the number. And then if you wanted to clear it, then you can use this. But first you want to get the number, then you want to clear it.
Yeah.
So that's a answer to question number 23. This is going to clear bit, this here is going to clear bit 0. Clear bit 0. So that's pretty cool. I like that. Let's do another one. So we did testing bit 0. We did clearing bit 0. Let's have a look at some of these other operations we can do. Right now, everybody should have a signal processing shield. The signal processing shield is got a chip in it, and the heart of the shield is called the MCP 4921. And the 4921 is a solid state 12-bit DAC made by Microchip. And so what we're going to do is we're going to learn how to program this thing using the serial peripheral interface, which we have been studying in the past. And this is the reason why we've been studying it, because there are so many chips that make use of it. It's a high-performance synchronous interface. The chip itself is very convenient for us to do prototyping with because it's in an 8-pin DIP. 8-pin DIP has an orientation denoted by a mark that's an indentation on the package. It has 4 pins on each side, and the pins for all the DIPs that you will find in the stock room and this one are spaced by 0.1 inch. And what that means to you, the student, in this class is you can take the chip and you can plug it straight into a breadboard and then hit it with the DuPont wires and wire it straight to your Arduino, which is very convenient. So what you're looking to do for your basic DAC application is you're looking to get the pins. The pin numbering starts at the left and works its way like a U. 1, 2, 3, 4, then across 5, 6, 7, 8. The pins for a DIP are very convenient for your, I'll call it breadboard, but are kind of inconvenient for manufacturing, because when you are making a printed circuit board with the so-called through-hole pins, you have to drill a hole for each pin. And when you build one board, drilling 8 holes isn't so bad. But when you're building 400 boards, drilling 3,200 holes is a little difficult. And that gets tedious. I mean, how can I say it? That gets tired quick. So what you do,
Fast too.
Huh?
Drill bits wear out fast.
And the drill bits wear out because you're drilling through fiberglass and epoxy, and the drill bits break, and you have a thing called run out where the little drill bit wanders, and you have bad holes, and it's just, oh, it's terrible. And then you don't get plate throughs if it's not a professional bore. So what you do is you switch this out for something with an identical pin out, but with a different outline. And they call it SO8, for small outline 8 pin. And that is a standard which you can use for so-called surface mount technology. And what you'll do is you'll get something like a stencil or a machine that can lay down some solder paste, and you'll place the chip onto the solder pads and then run it through the oven, and it'll just solder them all up, and you won't have to drill any holes at all. The pick and place machine will shoot these things out like a machine gun, and they'll do it on a giant panel full of chips, full of boards, and then you have a whole bunch of boards, gesundheit, being made all at once. Gesundheit. So what you want to do is you want to get to the data sheet, and I put the data sheet up in the homework so you can look at it. But essentially what it looks like is this. This here is power, plus 5 volts. We call it VCC. You got ground in pin 7. And 5 is a reference that comes in that says not back, and you ground that as well. This is LDAC. You just ground it. There's a voltage reference that comes in. I'm going to get rid of these little wires that show 1/10 of a volt right here. What we'll do is you can use an outside and external voltage reference, if you like. In other words, the DAC can be floating around 0 volts and go plus or minus 1 volt if that's what floats your boat. But if you put it out to VCC, what will happen is the DAC will go from 0 to 5 volts, which is just fine. And then there's a voltage out, the out. And that goes into your amplifier, which then goes into your speaker. The other end of the amplifier goes into ground. And what you want in here is a chip select. This is an inverted chip select. You'll need your serial clock, and you're going to need your serial data in. There is no serial data out. And that's the interface to the chip. And that's an SPI interface, which goes straight to the microcontroller. And by the way, this will work with any microcontroller. Any microcontroller. But we have a nice library for the Arduino. And question 1 asks, can you drive a speaker directly with the DAC? And the answer is no. It cannot sync the current. You need to have an amplifier. If you were to plug your headphones, real 8-ohm headphones, directly into this DAC, it would sink way too much power, and it would blow out the DAC. So you got to kind of be careful. What you want to do is you want to use your PC speakers, assuming they're amplified, and then you're okay. Or you could use very tiny earphones, maybe for an iPod or iPad. But you don't want to try and drive real speakers with this thing. It's not going to go well. So iPod headphones will work. Don't try and drive. You know, it's a standard stereo connector. It's a 3.5 millimeter connector. You can plug things into it, but don't just plug random things into it. So that's question 1. Question 2 asks, is this a 10-bit DAC? And the answer is no, it's 12 bits. And what does that mean? What does it mean in terms of, you know, dynamic range? Well, what it means is, I have 2 to the 12 as the number of quantization levels. How many quantization levels is that? How much is 2 to the 10? Okay, how much is 2 to the 2? Chris?
4.
Okay. 2 to the 3 is 8.
1023, isn't it?
1023. 1024 is 2 to the 10.
Yeah.
So 2 to the 10 is equal to 1024. 2 to the 11 is double that, 2048. 2 to the 12,
4096.
4096. Yes, that is correct. So you have 4096 different levels. And what that means to you is that you have a quantization noise, V sub Q, which is equal to 5 volts divided by 4096. That's your quantization noise. That's a number. I don't know what the number is, but it's relatively small. I can tell you what the number is. I had a calculator on my little iPad. Actually, you guys have calculators, don't you? Oh, maybe not. So anyway, it says here that 5 divided by 4096 is equal to 0.001 volts. So that is the 0.001 volts is your voltage of quantization. That quantization noise is the noise that you can, the minimum noise that you can detect, the minimum voltage you can detect, and, or actually produce, minimum voltage you can produce. And if you think about it, you might do better if you essentially made the full deflection go from 0 to 1 volt instead of 5 volts. So here's the other aspect to all of this. We have a signal to noise ratio, which is equal to 6 dB, that's decibels, times the number of bits plus 3 dB. And so in principle, we should have something like 12 times 6, which is 2 carry the 1, 6, 7, 72, maybe 75 dB of signal to noise ratio. That's the best you can do with this DAC. So it's going to be a DAC that has a little noise in it. Every DAC does. Every DAC does. And there is another aspect to this. Now we have the dynamic range. What about the speed of the DAC? And by the way, this is the answer to question 2. So the clock on the Arduino Uno is 16 megahertz. Does that impact the speed of the DAC? Does that mean the DAC can run at 16 megahertz? Does that mean the DAC needs a 16 megahertz clock? And the answers to both is no. The DAC doesn't run at the CPU speed, nor does the DAC have anything to do with the CPU clock unless you want it to. The DAC is a successive approximation A to D converter. And what that means is you've got a counter in there, and the counter can have its own clock. And the maximum rate for the clock that feeds the 4921 successive approximation DAC is 20 megahertz, according to the data sheet. In other words, it has nothing to do with the Arduino Uno's maximum rate. What does impact the maximum rate that you can output is how fast the Arduino Uno can pump data into the DAC. Now that is something that's going to affect our sampling rate when we do a waveform reconstruction. Now that 20 megahertz clock, does that have anything to do with the sampling rate? That's the clock it wants. As it happens, if you want to do a full 12 bits and guarantee the output to be settled, it'll settle in 4.5 microseconds. A microsecond is 1 × 10⁻⁶ seconds, so that's a millionth of a second. So if the DAC has a 4.5 microsecond settling time, what is the frequency of sampling maximum? And the answer is 1 divided by 4.5 times 10⁻⁶. And that comes out to be a number that runs about 222 kilohertz. So that's an upper limit. So now we've got 2 upper limits on the device. The dynamic range, it's a 12-bit DAC. The settling time, 4.5 microseconds. Now, if you're dealing with audio is got a range which goes from 0 to 20 kilohertz, or thereabouts. If you're dealing with a Nyquist sampling theorem, you have to sample it twice the highest data rate you plan on reconstructing, at a minimum. So at a minimum, we'd like to sample at 40 kilohertz. And I'll write S sub n for Nyquist. So how fast is that? Let's take a look. 40, let's see. We'll do it this way. 1 divided by 40000 equals, a period for Nyquist is going to be 2.5 times 10⁻⁻1, 2, 3, 4, 5, 6. It looks like 25 microseconds. So the DAC is capable of doing 4.5 microseconds, but even if you wanted to sample at 40 kilohertz, you'd only need 25 microseconds. And 25 microseconds is, well, perhaps an order of magnitude slower, and that kind of makes sense, than the 222 kilohertz in 4.5 microseconds. In fact, if all you wanted to do was voice, you could go from 0 to 8 kilohertz. That would be the bandwidth for, we'll call it a voice grade phone line. And so if all you want to do is record your voice, then in principle, you could probably stop with a sampling of 8 kilohertz and just go from 0 to 4 kilohertz on your maximum output. Most of the energy is going to be in the lower frequencies anyway. So if 8 kilohertz is all you really need for your sampling, that says to me, you only need 1, 2, 3, 4, 5, 6. You only need 125 microseconds. So check it out. We've just gone 2 orders of magnitude slower and have decided that we can do a nice sustained sampling, which will get us out to 4 kilohertz of audio if we sample once every 125 microseconds. That's pretty good. That's pretty good. Now, not to put too fine a point on it, let's assume I have an Arduino that runs at 16 megahertz. Okay, 1 divided by, let's see, 1, 6, 0, 2, 3, 1, 2, 3, equals 1, 2, 3, 4, 5, 6. Really? 1, 2, 3, 4, 5, 6. Yeah, 0.06 microseconds. That's the clock. So a 16 megahertz crystal in the Arduino is doing 1 clock cycle every, we'll call it A for Arduino, 0.06 microseconds. So Arduino is way faster than this sample rate right in here at 125 microseconds. And I like that because I need to actually take the data and process it. And I need those extra cycles to do the processing in between samples because I can't store a lot of data this way because Arduino just doesn't have that much RAM. So if I'm going to do signal processing, I need to have a reasonable ratio of sample rate to processing rate. And that's a pretty good ratio because what that tells me is I have spare cycles to work on the sample after I've sampled it. Because if I don't have that, then I can't do very much in the way of signal processing. Is it making any sense? In other words, you want a CPU that has sufficient bandwidth so that you can actually do something with the data as it comes in. Because you have to, when you do this kind of signal processing, you basically don't get you can't just store it and process it later like a batch processing job. You've got to do streaming processing. So that's the answer to question 7. We got the range on the 4921 DAC. Let's assume for the moment that I want to build a wavetable. So what's a wavetable? Wavetable. Let's assume for the moment that taking the sine of theta takes too much time. So I'm going to pre-compute the sine of theta for increments in samples. So what I'll do is I'll take the sine of theta and I shall digitize it into an array of 0 to 511 locations. And I choose this because I know that even if I use 16-bit quantities, I'll be able to have a wavetable that can hold an array of 511, let's say, short integers. And I'm going to store the sine table in there somehow. I know sine gives me a number, right? It's a float. I'll call it theta equals sine. Let's call it some kind of an increment. Well, I guess we'll do it this way. I know how to do this. Sine's output will be a voltage. The input will be an angle, theta. And the voltage will have a range between -1 and +1. And what I want to do is I want to scale for my DAC a number that goes from 0 to 4096. So what do? I say V equals V plus 1. Now I've got something that ranges from 0 to 2. Then I take that quantity and I multiply it by 2047. And now I have something that ranges from 0 to 4096. And that conditions the output so that A, it can be put into this array, and B, so that I don't have to do any scaling before I pump the numbers out to my digital to analog converter. So I'm going to take this 512 sampled sine wave, this high precision 16-bit sampled sine wave with 512 samples. I'm going to clock it out to my DAC fast as I can at 212 kilohertz. That's as fast as the DAC can handle it. What frequency will I be creating? How would I know? Can anyone help me compute that? What is the frequency of the sine wave that comes out of the DAC when you have a 512 wavetable being clocked out at 212 kilohertz? Right? In other words, I've scaled the voltage, I threw it into a sine wave table, pre-computed the whole thing, so it's pay now or pay later. I'll do that in the setup. And now I want to just chug it out to the DAC. What do I do to compute what the frequency will be? I should be able to know that, right? Well, I'm going to get one sample every 212 kilohertz, but how long will it take me to do 512 samples?
Well, that's a sample rate. So if you multiply it by the number of samples.
Yeah. So I know that the frequency of sampling divided by the total number of samples is going to be equal to the frequency in hertz. Right? So what I do is I take total number of samples, 512 samples, and I will take this entire wavetable and clock it out once every, let's say 212, 212, 000 hertz. And so that's probably something like 400 and a fraction, 435. So let's take a look. Take 212,000, divide by 512, and you get 414 hertz. Isn't that right? Oh, it's 222 kilohertz. I got the wrong sample rate. 222.
You get 434.
222,000, and now I'm going to have a sample of a nice sine wave at 434 hertz. 434 hertz. Let's assume we want to go the other way. Let's assume that you really wanted to have a tuner, and the tuner has to give you, let's say, 440 hertz. So, and you know that 222,000 divided by the wavetable size and we need to know the wavetable size. And so we wanted 440 because that's the frequency of a concert A. And so what we do is we take 222,000 and divide it by 440, and we get a number, and we need 504.5 or 505 samples. So if I go at this sample rate, 222 kilohertz, with 505 samples, then I'm going to get very close to an A440. Will it be exact? No. How far off will it be? Well, let's see. 222 kilohertz divided by 505 will be equal to 439.6. That's pretty close. 439.6. Not exactly 440, but close enough for government work. So now I've got essentially a tuning standard, assuming that the 222 kilohertz sample rate is accurate. So there you go. You can output frequencies that you can hear. You can do it with precision. happen to me if I wanted to go up an octave, right? Suppose I wanted to go to 880. 880 is exactly 1 octave higher. What would I do with my number of samples? And the answer is I cut it in half, and I get 250 plus 252 samples. So if I cut from 505 down to 252, I'll be going at 880 hertz. And that'll be a high C. No, high A, concert A. So that's that. Any questions about the sample rates and the frequency? You're going to build a synthesizer in the lab. It'll be an arbitrary waveform generator, and you're going to use this concept, which I will outline for you briefly. So that's the basic idea. Let's take a look at how we can create a wavetable using a buffer. So what I'm going to do is I'm going to use unsigned 16-bit integer quantities, and I'm going to call it U. Oh, that's not a good color. INT 16 underbar T. That is an unsigned 16-bit integer quantity. And I'm going to call my digital delay wavetable 512 and put in a semicolon. What this does is different from what you might be used to in Java. What this does is it allocates 512 16-bit quantities, which is going to take you 1,024 bytes out of your RAM. And that's actually important because you don't really have that much RAM. And now what we're going to do is we're going to pre-compute the sine wave. And we'll fill the sine wave with a method called fill sine wave. And so now you need to come up with an increment for theta. Theta is going to go from 0 to 2 pi. So what we'll do is we'll create a float for delta x. This will be the independent variable. And we'll set it equal to 2 times pi divided by 512. And what that does is it'll allow us to increment theta by 512 times and make sure that we have a theta that is actually going to essentially move the sine wave from what we call this part of the cycle, beginning to the end. So this will be theta is 0, and here's theta at 2 pi. And we'll go in 2 pi divided by 512 increments. And so then what you want to do is make a little for loop. And you need an index. And that's going to go to the entire length of the array. And what you're going to do is you're going to want to get a sample out of the sine wave and condition it. A couple ways you can do this. What I'll do is I'll just say FD equals 2047 times the sine of, we'll call it the frequency counter, if you like, or your theta. Then we'll take the frequency counter and we'll increment it by dx, where dx is equal to the epsilon that you're using for your theta. And then what you want to do is set your output waveform, dd, is 247 plus fd, right? Because sine is going from -1 to +1. Now it's going from -247 to +247. So we increment by 247, and now it's going from 0 to 4097. And then that fills up the sine wave. Now it'll create a sine wave for you. So the range, what's the range going to be for DD? It's going to be 2047 times 2, which is pretty close to 4096. It's probably 4094 or something like this. And that is the answer to question number 9. All right, so who's getting lost? Anybody out there in Zoom land getting lost? There are people here, right? Just looking. Well, we got a bunch of people here. People on Zoom, that's good. That's good. So if you're going to do SPI programming in your DAC, you're going to have to include the SPI functions. And there's a macro invocation for that. And that's going to give you access to a series of different invocations that you can use. For example, you'll be able to do SPI dot, and then issue commands to the serial program peripheral interface. For example, you could say SPI set data mode. And what that'll do is you might say SPI mode 0, that's built in. You'll be able to take the clock of your Arduino and divide it down. Set the clock divider. And this is using a built-in clock built into the CPU. Take that 16 megahertz, and you can divide it by 5. What's that give you? Some kind of an interesting number, I imagine. 3.2 megahertz. We know the clock rate for the DAC can be up to 20 megahertz, but we can run it slower if we want to. Then comes this other thing which is kind of interesting, SPI set bit order. And I don't know if you recall when we talked about Little Indian and Big Indian. The this is going to do the most significant bit first. And that's important because we're shifting the bits out one at a time, and we have to know which bit is coming first, the least significant bit or the most significant bit. We do the most significant bit first because if we decide that we're only going to have an 8-bit DAC instead of a 12-bit DAC, we may only want to shift out 1 byte at a time. So we might just shift out the 8 most significant bits and let the rest go to 0. The other thing you do once you set this up, this is just like setting up a serial port. And you could do this in the setup. Let's do an SPI.begin, just like the serial port. So when you're doing programming at the low level, you need to do the MOSI and the MISO outputs and inputs, but you have to establish the serial clock. And that serial clock is the clock that is used for communicating with the serial peripheral interface device. And now what we're going to do is we're going to set the LDAC port B bang equals to 0B 000 000 11. And now you can see what this is doing, right? Because we discussed that before. And in fact, that is very similar to what we saw in the first questions that we went through. This is essentially going to set bits 0 and 1, setting them both. And what that does is it sets the chip and the LDAC to the default high state. So this is more bit flipping. And sets bit 0 and 1 on port B. If I had an Arduino, I'd hold it up and show it to you. Maybe I do. Maybe I do. Now that I think about it, I thought I saw a picture of an Arduino in the prior homework. I don't have one. Port B. Yeah, they don't label the silk screen on this particular version of the Arduino, so it's not going to help you. You have to know which pins are which. That's not good. All right. After you're done with the setup, you can call, as part of your setup, fill the sine wave. And once you're done filling up the sine wave and setting up your SPI ports, there are a few other things you need to do to establish the timers and the interrupt. The goal here is to use the interrupt in order to be able to tell the Arduino when to get another sample and put it into the data port, that is to put it into the SPI. Meanwhile, in between interrupts, it can do other things. So when you have interrupt-driven processing, what you expect is that the Arduino is going to be busy doing a lot of other things, because we know there's like a 100 to 1 or even a 1000 to 1 ratio between the Arduino clock and the sample rate. And so what we'd like to do is we'd like to let the Arduino do something else in between samples. So we'll set up a clock to trigger an interrupt that causes us to pump out more data to our DAC. And there's a little detail there, which I'm not going to go into right now. Suppose I wanted to divide this by 8. What would the SPI clock rate be? And this is a question that's for question 11. And the answer is if you divide it by 8, SPI clock divided by 8, this is going to be 2 megahertz for an SPI clock. And that's the answer to question 11. Let's see what else we got here. I think it's obvious what the most significant bit first means. That means data is shifted in with the most significant bit first as they shift into the SPI. And that is the answer to question number 13. I don't know if it's obvious to you when you look at it, but there it is. I mean, it says MSB first. And what you want to do when you want to learn more about the details of SPI is you want to look at the reference implementation in the Arduino, and that's a part of question 12. So question 12 has a URL, and you should look that up. And when you do, you'll find the answer to question 12. And it asks the question, does the SPI work on an output edge or a data edge? You'll be able to look at the reference implementation for the SPI and you'll get that detail. And yes, indeed, when there is a falling or rising edge, SPI makes a change. So that's kind of an interesting idea. You want to know exactly how SPI works, you look at the reference implementation. You look at the URL in question 12. Let's see what else we need to know from this. I'm going to skip ahead a little bit. And can somebody on Zoomland tell me why the serial DAC needs to have its own clock? I think you Zoomland folks are quiet, and then you should pipe in. Why does the, I'll call it the MCP 4921 need a clock? Why? Can somebody tell me? What kind of a DAC is this? Anybody listening out there? Somebody should say something. Make me feel better about myself.
Yes, I'm listening.
Yeah, good. So what kind of a DAC is this? This 4921?
I'm not too sure.
Well, this is a successive approximation DAC. And why does a successive approximation DAC need a clock? Anybody know? Let's take a look at the anatomy of the successive approximation DAC again. I know we did this once before, but I think it makes sense for us to look at it again. So what happens is you've got an analog signal coming in, and it goes into an op amp. The op amp compares the analog signal against another signal. You got a DAC over in here, and it outputs an analog signal. And that goes in. And when it's low, we want the register, this is the successive approximation register, to start to count up. And when it's high, we want the successive approximation register to start to count down. And so this could be 12 bits going into our little DAC. Here's our little output from the DAC. And when the DAC is chasing after this input signal, the successive approximation register has to be counting up or down. So it needs to have its own little clock. It's an up-down counter. And all we can do is choose whether it counts up or down. And what we can do is we can latch the output of the counter from here and feed it into a computer. So that's a successive approximation A to D converter, right? Now suppose you wanted to have your little DAC at the end of a serial port. DAC is parallel. Here comes a shift register. Here comes the data. So that's, we'll call it master out, slave in, MOSI. The shift register needs to shift at a specific rate. So it needs a clock. So here comes the serial clock. And then when it's done, it can strobe its output directly to the DAC. And now the DAC can give us an output. So we got to have a serial clock if we're going to have a synchronous transmission of serial data into our little DAC. All of this is contained inside of the MCP 4921 DAC. And so what we need to do as programmers is we need to write out 16-bit quantities to the DAC, and we're going to do it 1 byte at a time. And this is how you write a device driver for a little chip like this. I mean, you got to do it. You know, it may be done for you, but eventually you're going to end up doing it yourself. So here comes the DAC write. And what you'll do is you'll take an unsigned integer 16-bit quantity, and that'll be some part of your output buffer. And now what you got to do is you're going to change some bits at the beginning. You don't need 16 bits. So we'll say bang equals, actually that's a vertical bar, 0, I'll do it in binary, 0, 1, 1, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's going to set the most significant 3 bits in every case, but leave the least significant 12 bits alone. Then I'm going to pull the chip select low, port B equals ampersand equals 0B 1111 1 2 3 4. Let's see, 1 2 3 4 5 6 1 2 3 4 5 6 0 1. So now what this does is it takes all of the bits in here and leaves them alone except for the first bit. That's going to be where the chip select is at. So I pull that low, and then I do my SPI transfer. And I'll take the high byte of the output buffer. Then I'll do an SPI transfer again. And I'll take the low byte of the output buffer. So you can see the most significant bit is coming out first, which is just what you wanted, and that's how you set it up. Now I got to go back to port B, and I got to pull the chip select high. So I do port B. Take that bit, pull it high, and then take port B, and I got to pull the LDAC low again. Oops. 1, 2, 3, 4, 5, 6, 7, and 0. So now the LDAC is low. And what that does for me is it allows me to communicate one bit at a time out to the MCP 4921 and chug out my sample. And all I have to do is call up DAC right with a number that ranges from 0 to 4095. And now I'm able to write directly to the DAC. And I can write whatever I want. And this will handle everything for me because I've contained the complexity of the bit flipping inside of the DAC write command. So I can just keep calling DAC write and write out samples. So what does this do over here? It sets the 3 most significant bits, right? And that is the answer to question 18. And we kind of saw this at the beginning of the talk, but now we can see where it's actually being used for the bit flipping for us to write a device driver for our little DAC. You know that anytime you find a chip that the Arduino ecosystem doesn't have, you have the potential to bring a Kickstarter project to market because people want to experiment with a wide variety of different chips. If you provide them with rudimentary software for driving the chips as well as the hardware, you can charge $20 for a chip that costs you 20 cents. But the fact is you package it with some kind of a driver and maybe a little bit of software to do something useful with it, and all of a sudden people will start buying it left and right. When we first made these things, we made 400 of them. And that was just for a 30-day sale on a Kickstarter project. So if you're thinking in terms of where you're adding value, you know, this is tedious work. Most people don't want to do it. But if you can master this sort of thing, you effectively can create wealth because you're not just making hardware, you're making software for driving the hardware. And if you can deploy it into the Arduino ecosystem, they will appreciate it by buying it. Now you just have to price it right. And for most of the people in the Arduino land, $20 is about right. And that's a lot of money for a cheap little printed circuit board. And this is basically all you need for a device driver. And after that, all the rest is applications. Maybe echo or flange or phase or guitar box sounds or whatever you like. So that's kind of an interesting idea. Being able to write device drivers with SPI interface, that's a critical skill. And the fact is, I think everyone here will be able to do that by the time this course is done. So that's what I've got for you for today. I hope you like my little presentation, and I thank you for your attentions. Stay safe.
Thank you.
Thank you. Thank you.
Thank you, Professor.
Thank you, Professor.
Thank you,
Thank
Professor.
you.
What you get for
So, disconnect, stop.